put some tunes on.
Okay, let's get settled down. Let's get started. So now we're going to have Granvik, who's going to talk about the interrelating physical and dynamic characteristics of asteroid populations.
Okay, thank you. Yeah, so I will talk shortly about, for half an hour roughly, about asteroid populations, especially the inner solar system, and after me, West will talk about the outer solar system. What I will be focusing on in this is now what we can actually learn about asteroid populations and what they would like using LSST data and what that data can teach us about the physics of these asteroids. It's something that we've understood only recently, and I'm trying to we'll give you a short example of what I mean. So the LSST science book from 2009 lists several research topics related to asteroid populations. And the goal there would be to, or the proposed research would be to derive a debiased orbit and absolute magnitude distribution for asteroids, connect, establish better connection between main-Earth asteroids and near-Earth asteroids, because these two populations are dynamically related. There's also suggestions about measuring fractional comments in the near-Earth asteroid population. And there's nothing wrong with these research topics. They are interesting still, and LSST can certainly put strong constraints on all of these aspects. But looking at it in 2016, it seems a bit like these research topics would be slightly outdated. So we're basically looking like in a rear mirror when we look at these research topics, because there's much more that LSST can do through this population model than what has previously been thought possible. Indeed, the scientific goal of constructing these population models is not just, or should not just be considered to provide numbers of objects in the population, or to understand links between different populations. But rather, I think nowadays it should already be, perhaps the even more important scientific goal should be to reveal our own ignorance about the real physics beneath those numbers. So when we construct more population models, we need to start taking into account the physics that go into those numbers. So recently we've shown that already contemporary surveys, the current surveys that are operating, and actually that were operating, the data that was collected until 2012, that is 10 years before LSST start survey, is already enough to allow simultaneous estimates to constrain your orbit and absolute magnitude distributions. If you constrain the interior structure of asteroids. This is a paper that we published earlier this year. I think this is really opening the venue to much more interesting science than just pure numbers, statistics of asteroids in the sky. So let me shortly walk through, or take this time to walk you through this example, because from this, I think this is a case example, but there will be, I'm sure there will be more similar results in the future leading up to LSST. So when you start modeling populations backwards, we start from a basic equation. This is a simplified equation, of course, but I call this an efficiency equation. It states that on the left-hand side you have first the observed population, which is what the observatory provides us. So we have the three orbital elements there, centimeter axis, eccentricity, and inclination, and then the absolute magnitude. And for this particular project that I'm talking about, we used the Catalina Sky Survey as the survey, which produced then this data. As you may know, it includes two different kinds of telescopes. One is narrow and deep, and the other is shallow and wide. And here's the data collected during about 8 years. So on the top panel you see the elliptic coordinates of detections, and you can clearly region on the sky, and also with the orbital elements and absolute magnitudes, as you can see on the bottom panel. So you have here the absolute magnitudes, inclinations, eccentricities as a function of sedimentary axis for these two surveys. So this is a substantial improvement from the model that was produced about 15 years ago by Belfast, who used about 100 objects, 130 objects. And here we use some thousands of objects already. So this is a factor of about 30 more. When LSST will come online, has carried out its survey, we will have about 20 times more data than is in these plots. So you can get an idea of the things that you could do then. And this is, of course, this new data is particularly important, not in the densest regions where we already have a bit good sampling, but in the less sampled regions, that's more Penigelia and in terms of the smaller objects or larger and absolute magnitudes. And the first on the right-hand side is the observational bias. This is, of course, estimated numerically for each survey that we use. I will just show some examples of the bias that we estimated for CSS. So in these plots, I have constant slices in constant inclination. So you have sedimentary axis and eccentricity in all of these plots. And then on the bottom, I have a slice in constant eccentricity. So you have, instead of eccentricity, an inclination here. And now the columns here are for the 703 survey that doesn't go that deep, and then G96 which goes slightly deeper, and then a combination of these which I'm actually using in the processing. So here when I start the animation, we start working from bright objects, so large objects towards smaller objects. You can see that it becomes gradually more and more difficult to find asteroids with certain kinds of orbits, as you would expect. Now, this is not really trivial, and there's a fair amount of systematics involved in here today with the current surveys, not least because there's always a human involved in the discovery process of asteroids. So PAMSTAS was going to be the first survey that was going to be run in a mode that humans don't intervene. It would be doing its own follow-up and just collect a sample of TNOS. Unfortunately, it never worked for various reasons. Among other things is that we had only one telescope instead of 4, as the original plan was. But LSST will probably be better off because it's pretty sure that humans cannot analyze the data that comes from or sort of start mixing into the analysis of the data. So we have this type of human component of, and probably also LSST will do its own self-follow-up. There will not be a survey probably that's capable of following up on everything. So we can focus on LSST data only, and that will allow us to use more accurate biases. The second term on the right-hand side is the true population, and this is, of course, what we want to really understand. And now, of course, there's LSST is proposing to discover, suggesting to discover about 100,000 NEOs. Peter will talk more about these numbers later on. But this implies that even with 100,000 NEOs, this, if you want to have a good resolution in this 4-dimensional model, 100,000 objects will not give you enough, large enough sample that could produce a high resolution model. So instead, we use orbital dynamics, and we slice this true population into an orbit component and an absolute magnitude or size component. I would call this size, although that's not strictly what it's actually saying. It's the absolute magnitude, but let's call this the size component. And the orbit component here can be pre-computed because we know fairly accurately how asteroids are dynamically evolving from the main belt here in green into the NEO region and then to the eventual death in either the sun or after colliding with a planet. So here you have black holes And this is their distribution at that point. And as you see, they are aligned along these mean motion resonances, and then there's also some strong secular resonances like the new 6. And now at this time, we classify these test asteroids that we integrate into different source regions. So I'll just color them here. So we have a new 6 region, stuff coming from the Hungarian population, Hungarian population, new 6, and then a number of different motion resonances. And now when we continue integrating these objects into the NEO region and track the time that they spend on different orbits to get these kinds of plots. So here we have now, you can clearly see from this that depending on where they come from, they have different distributions. And just to make sure that you sort of can track where they come from, so these red ones come from this distribution, the green ones, for instance, from this distribution, and so forth. And now the total NEO orbit distribution is a linear combination of all of these. These are the escape routes from which NEOs enter, the asteroids enter the NEO population, near the asteroid population. So now we have basically fixed, we have these from the telescope, this bias we estimate numerically, these we do orbital integrations for, so this term is essentially the only one that we need to fit for. And there we have 4 parameters describing a slightly more complex size distribution than a power law. With 4 parameters per source, for this modeling we use 7 sources, so we have 28 free parameters for this model. And here I show the observed histograms of parameters that we're interested in: centimeter axis, eccentricity, inclination, absolute magnitude. And in red, you see the predicted, which is the true distribution multiplied by the bias. So at the face of it, this looks good, which is not surprising because this was fitted. This is showing the data that we get and best fit. But if you look more closely, you can see that there is an offset, systematic excess predicted for small centimeter axis and large eccentricities, also an excess for large inclinations. And for a celestial mechanic or person doing dynamics, it's clear that especially these top 2 plots point towards something wrong with the perihelion distance. And indeed, if you look at the perihelion distance distribution, here in black I show the absolute numbers that were observed, and the red one is what we predict. So you see that there's a clear offset. And this offset is more clearly visible if you take the ratio of these 2. And you see that there's a factor of 10 to many objects roughly predicted for the smallest thing. Now, it turns out that these objects don't start disappearing. Okay, let's back one step. We did a lot of analysis, so we tried increasing the number of source regions and splitting the NEOs into even more groups or the source regions into more components. And this situation doesn't change even if you increase your number of parameters to 100. So it's a very stable result that this cannot be explained, and there's nothing we don't have any knobs to turn that we could make this fit better. So the only thing that you could do is to assume that they are somehow going away. Now the question is, how are they going away so that stuff starts disappearing at half an AE? That's outside the orbit of Mercury already. But it turns out that the perihelion distance doesn't evolve in time, doesn't evolve monotonically in time. So it's enough. So that means that the perihelion distance can go small and then go large again. So it's enough if you assume that the disruption happens, or whatever happens to these guys, is at roughly the error bar for this green line here, at the points 0.76 AU. And when you assume that, you get a much better fit with the observed distribution. And here's the ratio, and you see that it's given the uncertainties, it's pretty good. Very simple model, but it's a very successful explanation. And now if we look at the data with this model, now the data fits much better, especially you don't see any systematic excesses anywhere. Also, it's not that inclination is improved, although we didn't touch the inclination at all. So it's just getting rid of, somehow there are some high inclination objects, and I will shortly come back to this, and we get rid of them. You can then compare the resulting absolute magnitude distribution to some other recent results. There's some from by Alice and Abramo. We used to derive just the absolute magnitude distribution. Note that our result is a four-dimensional creature. So we have this absolute magnitude distribution, but we also have the order distributions. Then because of the way that we do this modeling, we can also slice up distribution, different size distributions for different sources. And now from this you can start doing try to do more physical interpretations of what actually happens at different sources, because for some reason the size distributions vary as a function of source, so there must be something different going on between these sources. And now because the numbers change, also the relative contribution of any from different sources varies as a function of age. So you have, for instance, the new 6 peaks here at about an age magnitude of 20, whereas the 3-1 resonance, the other major resonance is scaled out from the main belt, peaks about 23. And now because this changes, but the orbit distributions are pre-computed, they don't change with size simply because there is no strong effect from the size of the dynamics, especially in the NO region. Also, the orbit distributions vary as a function of size. So this is something that has not been the idea has been realized before, but it's only with this data that we can actually, this amount of data that we can start doing something like this. So we have not orbit distributions that depends on the size of the object. Okay, so coming back to the disruption mechanism, did some tests on it, or trying to understand what's actually going on by slicing up our data set into 3 size distributions. So we have this kilometer scale, 300 meter scale, and some tens of meter scale asteroids. And you can see from these fits that the disruption distance, which I just mentioned for everything, was roughly somewhere here. Now for the largest guys, it's a bit lower, but for the smaller guys, it's going to a larger number. It's of course roughly linear in this part. We can already immediately rule out from this that the tidal disruption by the sun is out of the questions and explanations why they disrupt, because we will need to get done here to cross the Roche limit. And this is really pushing the Roche, and this is for a very, very weak comment. They are also not evaporating because you need to be below this purple line and spend about 4.5 billion years there to evaporate directly. And these guys, even the large guys, spend only some thousands of years here. So it's probably not the diameter operation, it's also not on the silicon material. This is not a problem. Also, if you look at the temperature ranges, these are ranges calculated with slightly different methods, surface temperatures. You see that the temperatures are not that high. I mean, for instance, these smallest guys, so this is basically like not much hotter than that. So if you then think about what will happen to material in space, now let's see if this works. Okay, in this video, you clearly see, which you don't, that this slab of serpentine, when put in the solar furnace, there should be pieces coming off it. You don't see this, unfortunately. But I can just tell you that there is stuff coming off of it. So just by putting, heating something up by the sun, but this goes to a bit higher temperature, you can start doing weird things with rocks. So now, if there's stuff coming out, for instance, with this process or another process, you should somehow, that material cannot just go away completely. It must be somewhere. And now, if you look at the data from Meteor radars, this is from the Canadian Meteor Orbit radar. This work by Peter Brown and his colleagues. You see in this plot at the smallest perihelion distances now only that you have at small inclinations, and the function of perihelion, you have at small inclinations, you have a bunch of these red dots, which are meteor streams that have no obvious pattern bodies. The blue and green dots are objects with known pattern bodies. And now, a key feature of this plot is that because you're observing with radar is more sensitive to high inclinations. So we should see these easier than these. So there should be even more stuff here than what's on this plot now. Now if I put onto this plot where we could assume that the asteroids are disrupting, test asteroids fall here. So it's very likely that these red dots down here lack their pattern bodies because their pattern bodies don't exist anymore. They have come into like small pieces. And there's further evidence from Lisa Brown's team that you can actually find meter scale objects inside the orbit of Mercury. So everything goes into small pieces at that level. Looking then at the albedos, there was a few years back an unexpected discovery by the NEOWISE team who showed that these Athens, Apollos, and Almos are different NEO groups. You have here approximate orbital types that they have. The Athens come closest to the Sun, and the NEOWISE team showed that the albedo distribution for Athens-class asteroids is much brighter on average than the other types of asteroids. And when you plot, now look at this cumulative distribution here on the right-hand side. You see that if you divide asteroids into the high albedo in blue and low albedo in purple, we'll see that they have different distributions. This can be statistically shown to be different distinct distributions. And now if you take our models and look at different Q distributions for disruptions happening at different distances, you see that when you go from the purple to the blue one, the disruption distance increases. So if your purple is done like this is sort of obvious in some sense. Your disruption distance increases, and that's exactly what we see here. So this would indicate that the reason why NEOWISE saw this the albedo distribution shifting to larger albedos is not because there would not be darker objects there. It's originally. It's because the dark objects have shorter lifetimes. So these have the dark objects disrupt easier in a physical sense, and that's why they were not there. So there's nothing. It is brighter because it's missing the dark ones, basically. Now with the LSST, we can look more carefully into this, having also color information. So this has been done for SDSS here. It's an example where you can classify just based on photometric different color cuts. You can classify asteroids into C-type or carbonaceous to the best, or silicate-rich to best, or more sort of volcanic types of materials. Now, SDSS was basically a single epoch survey, or at least from the asteroid perspective. Now, with LSST, we also can make use of the fact that we will observe a large variety of phase angles. Phase angle is the angle between the source of light and the observer, seen from the target. So from this, you see that these curves are different for different kinds of observation, different kinds of asteroids. You can add this information into this and provide stronger constraint on the surface materials. And this is, of course, something that LSST will provide. So we will have probably stronger constraints on, for instance, the disruption mechanism, given both the accurate photometric, but also the fact that we have colors for everything. So as a conclusion, I would say that the orbit models that we have had so far for NEOs, for instance, have predicted too many asteroids with small Qs. And we didn't know this because we didn't have enough data. The data revealed basically that there is this problem, and modeling of the data, of course. And surprisingly enough, population models of NEO orbits at absolute magnitudes now provide constraints also on the interior characteristics of asteroids. this is sort of a paradigm shift in that this was, at least in asteroid science, it was typically two groups of scientists. Those who are focusing on the detailed physical properties of asteroids and those who are dealing with the statistics, the big picture. And now with this finding, these two sort of areas are coming together, and we can sort of both take advantage from both sides to produce even better results. And as I sort of tried to say, LSST will allow better models to be constructed in more detail because of a lot of samples, a survey that can be characterized, and then because these multiple classes and colors. And I'm certain that in 5 or 10 or 15 years we will look sort of equally stupid, if you like, as sort of the people that were now looking back for. Although the models were great, but there was simply not enough data to tell that they could sort of get all these great results. And our ignorance of the physics both below these asteroids or beneath these asteroid populations will certainly be revealed. So that's about it. Thanks.
Yeah, really seems all questions.
Is it non-gravitational forces that are responsible for different orbital distributions of NEOs of different sizes? What induces that?
No. I mean, the non-gravs in the NEO region is much smaller, is basically negligible because the planetary encounters dominate dynamics. It's the only place where we could have a difference, and we have tested this and constructed this model, is the way the objects are drifting into these resonances. But we did with one big numerical test to see whether we can actually see a difference. And with this data, at least, at the level that we are now, like a few percent uncertainties, we cannot tell those apart. So with LSST data, given that we have 20 times more data and sort of more colors and stuff like that, maybe we can start seeing some effects.
So is it fair to say that the current data sets tell us that the distribution depends on size, but we don't know why?
Okay, so there are, no, I mean there's maybe, this is something that always mixes up the things, but when I say that there's this, the orbit, you're referring to this orbit distribution changing as a function of size.
Right.
Right. Okay, so that's, sorry, I'm about to navigate on this. So this is the thing. So the orbit distributions are fixed, but the size distributions from different sources changes, right? So if you have a different size distribution, when you combine the orbit distributions, you will have different sort of relative importances, and that's what makes the orbit distributions change. Then if there's also an effect because these main belt objects will be drifting at different speeds, that then an additional correction, which at this level is not relevant yet. But it could be.
Okay.
I don't know if it makes sense.
You showed the nice slow colors and went on and said, oh, we can make phase angles, can be wonderful. The trouble is, of course, as you know, slow have data taken within 5 minutes, and LSST is not going to have that. So do we understand how to decouple tumbling light curves from color variation in the object? We also have this color variability in asteroids, we saw that in slow, from phase angles.
Yeah, so the rotation, that was of course, I mean, has been the same problem for past stars. And for the colors, now if you, I don't actually know off the top of my head how many measurements you will get for a single asteroid, but obviously over time, the rotational variations will average out. So, I mean, you might be getting slightly, but I don't know how accurate the colors will be. But
we must get about 200 observations per band after 10 years. But, I mean, for an object that's always visible, you get as many times as you get a static object.
yeah.
So junk that comes in and goes is a different maybe 100-ish. So you get 10 observations, sorry, you get root 100s, you gain only a factor of 10 by that. Is that enough to be useful?
It certainly is for non-tumbling ones, but tumbling and shape changes that occur with that are anybody's guess. But pick a favorite shape, tumble it, and see what you get. It's going to be different than another shape.
Okay, can the next speaker come up? We can have one more
I'll
question.
talk about that a little bit.
Okay.
Not so much.
So I mean, it's a big problem, but there will of course be the shaping version involved in this. So for like non-tumbling, which is rotating or primary axis, we'll get at least, or should get reasonable colors.
All right, let's step back again.
Everyone can hear me?
So now we have Wesley Fraser to tell us about the outer solar system.
Concise way to put it. Forgive me if some of this seems simplistic or maybe even naive. If you've been paying attention to the solar system and small body research for the last sort of decade, you would see that basically every small body population has undergone some kind of massive revolution, whereas, as Mikhail was just saying, we've gone from collecting observations to actually measuring physics. And so, of course, the Capital Sky Survey has done this for Meteors. I would argue that pan-stars and SOHO together are finally doing this for comets. The asteroids have been studied for a very, very long time. So we've been there for quite a while. Jupiter Trojans, SDSS really, I think, brought that along for us. Kuiper belts still waiting for that, and the simple reason is they're faint, really faint. Like for instance, a 24th magnitude source, we're only going to see about 10,000 of those with LSST. That's the total sample, give or take. I'm going to talk today more rather than focusing on physics, focusing on what LSST will and maybe won't do for the Kuiper belt. But while we are simple, we can at least provide nice animations because we spent a lot of time working on this sort of stuff. And so this is the outer solar system. This is actually the known outer solar system. All of these white objects are what I would call the Kuiper belt. Of course, belt is a bad name. It's more like a belt with a cloud or a fat belt or something. I don't know. You can see that there's a lot of objects that don't sit in this tight little ring right here. Of course, this is a belt, but there's a lot of stuff. There's a lot of structure to it here. Just to note, the Jupiter Trojans are these blue clouds here. There's actually only 1 in 10 of the known Jupiter Trojans are in this particular animation to give you an idea of just how many more of those we know about. And those are actually still faint too. So the Kuiper belt's in a pretty rough state scientifically compared to all of the other small body populations. So this is what I'm going to focus on today. Also, this gap here is not real, by the way. This is just a galactic plane propagating forward 30 or 40 years. This is, of course, where New Horizons sits. I believe that one right there, give or take, is Pluto. Of course, Pluto is one of the Kuiper belt objects. So we'll just run this forward a little bit. Ooh, whoops. Well, we'll go around to the structure. So this is a plot of eccentricity, inclination, and semi-major axis of the Kuiper belt. It doesn't look much like a belt anymore, does it? There's a lot of structure here. And so, for instance, this tail in eccentricity space, basically there's a line that cuts across here that we would call the interaction distance from Neptune. It's not quite Neptune's, it's not quite the perihelion distance of if you were going to cross Neptune's orbit, but it's close enough that Neptune's gravitational effect stirs you, and over a short period of time, you just kind of go away. And so this gap up here is real. This is just Neptune being a bully. Objects that fall into what we would call centaurs. These are objects inside of Neptune's orbit, maybe outside of Jupiter's. These typically last a few tens of millions of years before the gas giants who are the bullies of the solar system send these things out. But the really interesting stuff are not the temporary ones, but the long-lived ones in these fingers. These are the mean motion resonances, again, with Neptune. Neptune pretty much dominates all of the gravitational interactions out here. And this was the first hint that something exciting went on in the outer solar system at some point before we got here. are you stable. Once you're in a mean motion resonance, it's very difficult to remove you. You receive a small restoring force every time you go around the sun a couple of times, and it keeps you at that semi-major axis. So you see huge population here, at least a third of the known Kuiper belt is actually in a strong mean motion resonance. So that was really neat, and it took a couple of really smart people to figure this out. Let me show you this animation here. This is the original version of what we call the Nice model. It's because the people who developed this model were in Nice having beers when they finally had the aha moment. And so let's just start this. This is what I mean by exciting solar system. This is the initial solar system, at least according to this model. Note the semi-major axis here, 18 AU or so of the outermost gas giant planet, and a stable disk. Outside of it, again, note here, this is the inner edge of the known Kuiper belt, not the outer edge. So there's not a whole lot beyond that. And it's stable, a little bit of wiggling going on, but not a whole lot happens. So let's just wait. Kind of boring, right? But boom. And so what happens here is there's an angular momentum exchange between the disk and the planets, which are in this nice, compact, stable configuration. And without that disk, they would remain in that nice, compact, stable configuration. But the disk transfers enough momentum inwards to one of the planets, doesn't really matter which, wiggle around, get close enough, and then the whole solar system goes bananas, like it just explodes. And so 99% or greater of that material in the disk goes away, but that 99%, well, they're the ones that sacrifice themselves for us, because without that, the gas giant planets would remain unstable, the whole solar system would be disrupted, you'd probably get something that looks like a hot Jupiter rather than a stable system. That disk preserves Neptune going completely outwards, circularizing where it is now, and lo and behold, we're here. And so the Kuiper belt for a long time has not been so much a measure of what's actually in the outer solar system right now, but more of a probe of what has happened to the outer solar system. And of course, we're still working on that. That was a very simple version of what's been going on. We'll talk you through a little bit of that. But this is where my interest lies in the Kuiper belt. Hopefully we can use LSST to actually take us beyond using the Kuiper belt as a probe of other stuff, but actually talk about the Kuiper belt itself. All right. So the first sort of thing that has come out of studies like this, once we realize that there's a lot of structure that reflects the history of the dynamics of the middle and outer solar systems, we've been basically counting ever since, trying to get really good orbits to place objects in or out of mean motion resonances, because those are, of course, one of our best tools as an archaeologist to look backwards and figure out exactly what the dynamics were. And so this is a plot from the CPEP survey, Canada-France Ecliptic Plane Survey. We were never good with our acronyms. The idea was to use the CFHT to observe a few tens of square degrees and find a few hundred Kuiper belt objects and actually map out where they are in the solar system. So on the left, eccentricity, inclination, and semi-major axis observed. And then on the right is a monumental de-biasing effort comparable to what Mikhail has done for the NEOs. And you can just see, so there's a lot of objects in the Plutinos. These are, Pluto sits in this mean motion resonance here. And only a few detected things in the outer mean motion resonances. But you can see there's actually a huge population that we can't see. Barely see. LSST will still barely see these things. And that's only a measure of what we can barely see. We actually have very little constraint on what's going on here. So this is actually, I think, one of the things that LSST is going to help us with. Because even with just a few new detections of objects in 5-2, like they pretty much went from 2 to 5 at the end of this sample, we went from thinking, oh, well, okay, there's a couple random things out there, to holy crap. In fact, there's more objects in 5-2 than there is in 3-2, which means there's actually probably a huge reservoir of mass. Well, huge, 1/100th of Earth mass out here. Huge reservoir of mass that we just don't see yet. And so that, realizing that, has made us go back and rethink the exact path that Neptune and Uranus took when the solar system exploded. So this is the first thing that LSST is going to do. We're going to take the known, well-characterized sample of Kuiper belt objects from a couple hundred to a few thousand. I guess 4,000, but that's of course me guessing, estimating maybe based on the current known sample. Again, who knows what the heck tech is out here. We're starting to discover a few things out here in various running surveys, but really, LSST is going to crack open a lot of that for us. This is where the naive part comes in. I can't tell you what LSST is going to see out here because we just don't know what's there. It could be huge, it could be completely absent. So we'll see. Now, one of the next most fundamentalist things you can do with a sample of small bodies is just count their sizes, right? Not just the numbers, but figure out how many big things and how many small things there were. You never leave your thesis behind. This is what I did a few years ago. Unfortunately, we still don't know what the heck we're talking about. We can't, most people would look at a measure of the size distribution and try to relate that to an accretion history. We're not there yet. It's very clear that the basic, naive, hierarchical growth of small things, the bigger things, planets, actually doesn't work for the Kuiper belt. But something better, well, I'll give you a hint of what it might be in a bit. But for the most part, all we can really do right now is use the size distribution as another probe of where these things came from. And the idea is pretty simple because there's so little material in the outer solar system, and I mean little, there's at most 0.01 or a few times 0.01 Earth masses in the entire volume of the outer solar system. They don't evolve. Once they're there, they see one collision maybe that would affect their size during the entire 4 years since they got there or thereabouts. So the size distribution has actually been frozen in because of that explosion. And so we can actually use the size distribution of this population to relate it to other populations. And so these are a couple estimates of what they might look like, a couple simulations here from Granvik. I want to show this is the sort of what you would naively expect, a power law with a rollover. This is where collisions were happening in the disk before that explosion, and then this is all the small fragments and things afterwards. Depending on how violent you are, how hand-wavy you are in your simulations, you can produce this thing called a divot. There's a hint of that there, and this would be a real sign that that disk was extremely massive. So we'll talk about that in a little bit, but this is the current state of the Earth. This is what I got published a couple of years ago. I'll walk you through this here. Top is cumulative, bottom is differential, h as a function. So h is our absolute magnitudes here, because of course we don't measure sizes, these are unresolved objects. But roughly speaking, this here is about 100 kilometers or 200 kilometers diameter, give or take. The red things are the dynamically excited things. These are objects that we know have been put into the Kuiper belt after the explosion. And then the blue things are what we call the cold classicals. They appear like they formed where they are, which is kind of neat. Not everything got pushed into the other solar system. And you can see just by looking at the scheme of the plot here that at the large end, they don't match. They don't look like each other. That is statistically significant forcing or something along those lines. There are two separate populations in the Kuiper belt. One that got pushed out and one that remained in situ. There's other lines of evidence that tell us that they remained in situ. That's one of the important takeaways that we've learned about the structure of the outer solar system. Moreover, and probably even more important, the Jupiter Trojans here, the yellow ones, match this population, this pushed out population. And you would think about it for a second here. Jupiter sitting along, not doing much, and all of a sudden kind of went. Everything that's loosely in the top of Jupiter's pockets, i.e. the Trojans on either side, are just going to kind of fall out and remain over here, right? And so that happened. You put Jupiter Trojans down and you run this explosion in the solar system and they all go away. But because Jupiter was eccentric for a little while, it's got big arms, it grabs a few things, and stuffs them back in its pockets. Those are the Trojans. Just so happens that the same process is what populated the outer solar system from Neptune, basically doing a very similar thing, and they all came from the same place. So the huge population of mean motion resonance objects that we see was the first hint that Neptune moved. And that the fact that the populations in the middle solar system of those Trojans and the Kuiper belt objects have the same size distribution is proof that the motion was violent and occurred all the way from Jupiter outwards. Right? This is actually a really big surprise, not surprise, it's an important result to show that it's one of the things that you would predict from an explosive model like that. Now, this is what we'll get if you take the sort of best fit size distribution of the excited things in the Kuiper belt and figure out what LSST is going to see. So something like 10,000 points in here. So we're actually going to go from having a rough estimate of the size distribution, which I would still call it rough, that we can link to other populations, to actually having the size distribution itself, which is important because that's going to tell us about the accretion history. Right? It tells us how violent the collisions were, how much mass there was, how long it accreted for, these sorts of things. But talking about that divot, if you take a rough estimate of the two different size distributions here, so this is the one that I showed before, and then here is what you might get if you were to model a violent accretion history, and then contingent on what LSST will see. You see this divot here. Now there's a couple groups that are arguing with much effort that this actually exists. I don't know. I don't know if the statistics are there yet. There may be a divot in the size distribution. That would be really, really cool, because the only way you do that is if you put most of the accretionary mass at large things, not at the small end. So we're not talking meter-sized things that grow up to be large boulders, that grow up to be kilometer-sized things that then grow up to be Plutos. We're talking about dust that skipped all that and just immediately went to Plutos and slightly smaller things. And then you get this distribution of collisional fragments afterwards with nothing here because nothing grew to that size. There is actually a hint of this and reason to believe that this process actually occurred. So I think this is actually going to be one of the sort of revolutionary moments for us TNO guys with LSST in our solar system, because we're finally going to have the statistics to actually look at this feature, not just waves and things like we see in the Astronomical. I'm really, really excited about that. I've been talking, I mentioned that we're a bit naive about the Kuiper Belt. Well, it's certainly true that we have no idea what it's made of. For instance, we've never detected a silicate in the Kuiper Belt, even though densities of a bunch of these things are greater than 1. We have no hint what that silicate might be. We have no idea how much of it is there. Even after the damn New Horizons flyby, we didn't detect a silicate on Pluto. So we just don't know what they're made of. It's a simple way to put that. So we're still working on colors, and it's haunting me working on colors. For 5 years, I thought this would be done. I thought I would even be able to tell you what the TNO taxonomy is, but we're so far behind the asteroid belt, we don't even have a taxonomy at this point. One person will say one thing, another person will say another thing, and then 2 years later, they're both proven wrong, period. So this spectrum here is a very good spectrum, by the way, just how faint these things are, and it shows you how difficult this is. So this, I don't remember which object this was. Oh, sorry, that's supposed to say just Berucci et al. But the spectrum of these things are linear in the optical range. They roll over to something flat at around 1, and then they have some amount of water ice absorption, which is featured here and featured here. And yeah, those are real features. This is a really good spectrum. This is as good as it gets. We can detect water. Maybe if we're lucky, we can detect a small hint of methanol. And then everyone, take a guess. We really don't know. We speculate that this slope here is organic in nature, because if you were to take a hydrocarbon out of the ground or look at your skin under a spectrograph, you would realize the redness is actually due to what we call the organic gap, which is basically UV absorption of hydrocarbons that centers itself around here somewhere. And coals and bitumens, these really complex organics, are they're long chain, and so that feature is wide. And if you make a feature wide enough, if you make a Gaussian wide enough, it appears linear, which this appears linear, so the story fits, but it's just a story, folks. We have no idea what these things are actually made of. Unfortunately, LSST isn't going to do that, but beforehand, LSST will give us a taxonomy, I think. One of the things we do know is that there's at least a couple, maybe 3, probably 3 populations of surface types. And you can see there's just 2 of them showing up in color. So this is a plot of, again, H, or absolute magnitude, size versus color. And you can see this clump of scatter going on here, which we really have no good constraint on, nor would we want to try, because this is about the same size as processes like differentiation and volcanic activity, or cryovolcanism may alter the surfaces, so we don't want to think about those yet, because it's just way too complicated. Down at the small end, where things wouldn't show to differentiate, we see this gap where there's 2 separate populations that occur, and it's suggesting to us that that initial primordial disk actually had only 2 compositional classes inside it. objects and finally put this thing to rest. Here we are. So this is something like E minus I. This is something like I minus J, and then this is a pair of filters that is sensitive to water ice, because we know water ice is there, so we thought what a good idea this was. And so down is more water ice, and the real conclusions that we came up with from this are three things. One is there's an absence of objects here. You're producing a histogram, you see them up here and up here. There's not too many things in between. That's a function of size. Again, just like the previous plot, you only see that bimodality when you're looking at small things. The colors are correlated. You can see that here and here, and then downwards here and here. It argues that, in fact, these are both just one class of object with a range of color. I think it's just because of the mixture of compositions, but any number of things, thank you. But the third thing is our naivety. We just don't know much about this population even after an expensive program like that. But we do know that we're going to expect to detect about 13,000 TNOs. Here's a distribution of a simulated distribution of number of colors of each of all of these things. You can see that U is basically just going to suck for Kuiper belt objects because they're red, and you think quasars are red, well, these are red. Y, again, is going to suck because they're faint, but we're going to get really good GRI colors. And so I think we might finally be able to put together a proper taxonomy. By good, I meant mean colors that are uncertain by no more than 0.05 magnitudes. So here's a simulated object. This has light curve, phase effects, which are not that much for Kuiper belt objects, and uncertainty, GRIZ. And there's 800 points here. This is about what we would expect from a typical decently measured Kuiper belt object. And then if we fit out the phase, at least you can get rid of that, you can see that they basically cluster all around the same point. And then if you draw a line back to zero phase, you can get an average mean color and an amplitude of the light curve. That's what we're going to get. That's it. That's for every single Kuiper belt object. This is the entire quantity of the measurement that we're going to have beyond its orbit. Is a measure of its color at zero phase. Now that might not be that significant, but for me that's critical because 13,000 of these is going to be at least an order of magnitude more than I currently have. Very quickly, I'm going to go through binary. This was supposed to be plots of binary Kuiper belt objects. Hopefully LSST's imaging quality is a little better than this. This is a few of these things, a few hundred of these things are very widely separated like this. Most of them look like this, where you see the secondary there, but the point is the result will from the ground. The idea that we think how these things form is that you start from a cloud, maybe a turbulent clumped cloud of particles that collapse under some gravity, and you get a couple binary sources that are bound that fall out afterwards. Roughly, I'll skip the orbital distribution because it's still pretty naive on that. The point is, these things are so loosely bound they act as excellent dynamical probes. We know they haven't moved very far, they haven't seen Neptune's interaction very much. So these are proof that at least some Kuiper belt objects form in situ. And the neat thing is, LSST is going to discover 600 of them and fully characterize the orbits of about 300 of them. So again, talking about revolutions here, this is we salivate for this kind of information because they're the best dynamical probes we have. Very quickly, we'll talk about stuff that we don't know out there. We're just learning now that things like Sednas, these are really elongated orbits. So this is a roughly 580 here. That's the Kuiper belt. We know about 6 of these things now, and they're all aligned in space. This is the evidence for Planet 9, or as some of my colleagues, Planet 9, because obviously it doesn't exist, is what they say. But, I don't know if it exists or not. LSST may or may not detect it if it's as large as some people say it is. LSST has a chance. I'm not going to bet on that one. What I did want to show was that LSST, unfortunately, is not going to detect any of these things. Maybe 1, maybe 2, maybe 10, depending on the size distribution, because, well, LSST, quite frankly, isn't actually going that faint. Our surveys have gone fainter than 24.1 in R, right? That's where Sedna came from. So, sorry, we're only going to see another few of these things. But one of the things I want people to think about is occultations. If we can drive that camera quickly, we actually have a chance at this. These things are moving so slowly at 1,000 AU that an object the size of Sedna, which is 1/4 the size of Pluto, is actually going to produce a stellar occultation that lasts about 35 seconds. So you will have a star, and then all of a sudden it disappears. It's just gone for a pair of images, and then it comes back. not centered in the pair of images, but slightly offset. So this is a simulation of that for 21, 22, 23, and 24th magnitude star. There's a lot of 24th magnitude stars, right? So LSST is going to be the first chance we have of characterizing large things at 1000 AU. I wouldn't necessarily call these sediments that are falling in. Anything that's on a circular orbit out there that we would never, ever, ever see in the history of telescopes, 35th, 36th magnitude things, we can see with occultations of the LSST. So this is something I'm going to be pursuing vigorously, I think. At the beginning, I was going to have a section of the difficulties in tracking known moving objects. These are the line staggers, bears of moving objects, basically discovering, tracking, and then contamination are the three things that we always lose sleep over. But having spoke with the Pan-STARRS guys, this is actually kind of solved, believe it or not. For me, anyway. I mean, the NAO's guys, the contamination of a much bigger trouble, but chemical objects in this sense are easy. But the one thing that I wanted to point out is we still have some improvement to make in typical pipeline that we would use. Instead of looking at an object like a chemical object, so this is Pluto's motion through a couple of years. This is opposition of observation A and B. You can see it takes this funny line. Well, that's because the Earth moves, right? If you remove the Earth's motion, this is what that ephemeris looks like. And so what these lines here, there's the black line, which is Pluto's actual ephemeris, which is now basically just a straight line, straight arc on the sky. And if you guess the motion of the Earth, if you guess the motion wrong, you get these slight wiggles. Now, if you remove that, put it at Pluto's very center, just because of the projection onto the sun, when you assert a distance, you get these circles. Instead of lines that jump around all over the place, like if you were pretending to observe from the Earth, you get these circles. It makes it very easy to say, okay, I found an object, it's moving across the sky, I'm going to assert that its distance is x. And then if I assert it wrong, I get a big circle on its follow-up observations. If I get it right, I get a small one. So this is a very computationally inexpensive way of linking objects together. I'm out of time, so I'll keep it short. This is going to be something on photometry, and I don't have any time to talk about GPUs. Unfortunately, thank you very much. Astronomers don't communicate well enough. Had I known what you guys are doing with PSS, I would have started this conversation a couple of years ago. I'm running a photometric survey on Gemini to get colors of a couple hundred chemical objects to a few tens of millimeter precision. To do this, you actually have to understand the PSF of the moving thing, right? Not the star. I don't care about the stars. They're just they're my vermin. A galaxy is actually my vermin. To get the PSF, though, you actually have to put in some effort. And so I started with stellar PSF. I convolved that with a straight line, which naively turns out to be actually good enough to get your effective aperture correction and an informed aperture shape down to 1% photometry. And so with something like this, it's just a simple line convolution of a lookup table and a motley profile, you can recover 1% photometry. And so I found out yesterday that something along these lines is already being implemented in the LSST pipeline. Whether it's exactly what I would want or not probably doesn't matter all that much. But the point is, we can do better, just like with the linking and tracking and stuff that I was showing you that was courtesy of Matt Holman. This stuff that I invented here, or invented on my own here anyway, is something we really should do, because otherwise, especially in the signal to noise 10 to 20 range, you're throwing away so much information by using ground apertures, which is essentially what the last 20 years of chemical development observations have done. So, yes, well, I'm young, it wasn't me.
So let me just quickly respond. There is a place called community.lsst.org where you can ask any question that might come and you will get answers.
Yes, I was introduced to this at about 4 o'clock yesterday.
Okay. Thank you.
Mario?
So, how deep do you need to go to find more sediments? You said 24.5 is shallow.
Let me ask you the real version of that question. How far do sediments go? The sediment was discovered over 580 centimeter axis. It was found that assume everything is in the 500 AU range, we really don't know where they would be along those lines. My guess is, if this planet 9 idea is correct, there's reason to believe that these things have some major axes that go all the way to about 1000 AU, because that's where the influence of this thing falls over. And then, not only involving an unknown eccentricity distribution, we really don't know how far out the mean distance is. If they go out as far as 1000 AU, there is no, in a couple generations of human lifetime, there's no way we're going to populate that or guess at what that population is, because we can't go to 34th magnitude. If we could push LSST down 2 magnitudes with an appropriately aimed large deep drilling, then there's a hope that we can find a few dozen of these things, is my guess. That's a guess. But we're talking about many tens of square degrees to do this, because there's just not that many of them.
Yeah, it's two magnitudes maybe, but I was worrying more about, since we're going to have multiple observations of the same field in any given night, if stacking would help.
Deeper will help. Half a magnitude will help, but let's put it this way. Mike Brown, Mike Schwann, and I have observed with Subaru something like 250 or 300 square degrees to a magnitude deeper than LSST is going to go. And the number of objects we found is countable on this fist. So,
How large is many? You said many tens of degrees.
that's a good guess, or a good question, and it's total speculation. I would probably want to go with something like 6 deep drilling pointings. That would be a good start. I don't know if we'll find anything in it, but that would be a good start.
All right, can the next video come up? Are there questions from this side of the room? Sounds like that. Okay. All right, let's thank Wesley again.
Basically, I'll be talking a bit about meteors and how to detect them on astronomical images. I'll try to present what I did, but that was mostly based on SDSS images. And the LSST project is inherently different, so a lot of it won't translate directly to LSST, but it is possible to adapt it to work on LSST even simpler than it was to do it on SDSS. So because I'm not sure how much the audience is familiar with meteors. Just a short introduction. The meteors are the light phenomena that occurs when a meteoroid impacts the Earth's atmosphere at anywhere between 20 to 70 kilometers per second. They happen between 7 kilometers in height to 120 kilometers in height, and usually made for a really, really good show on the night sky. Through the history, they were usually observed visually. The National Meteor Organization has been collecting the data on meteors since 1988, I believe. The prominent orbits, which is what primarily interests the IMO. But they are trying to get rid of that bias that the cameras have, which is a very, very shallow magnitude, by introducing different kinds of observation, including radar, microparameters, and even telescope observations. But none of those fields have really been the primary interest in meteor science, and they are still very, very poorly developed, so to say. They are still handing out these kinds of charts where they are expecting people to actually visually observe through binoculars or telescopes and chart the seen meteors manually on the charts, which is kind of not appropriate for 2016. There's the first automatic meteor observation post that has the telescopic capability was developed somewhere in 2005, and it's the main automatic meteor observatory that boasts a telescopic way to observe meteors, and that's basically it. They're still very limited as far as the magnitude goes. They can, once they stack the detection, they can get to star magnitude of about 9, but of course for a moving object, that's a lot less. So what I try to do is to use sky surveys and search for telescopic meteors imaged in them. This one such meteor observed by SDSS in IR and G filters. This is a very bright one. So it left quite a prominent dust trail behind, which lasted for about 4 minutes. And the reason I started with SDSS is obvious, because their meteors tend to appear on random positions in the sky, and even though some meteor activity can be predicted annually to be increased in some certain period of the year, they can also happen sporadically, so long observation times are also necessary. Just a quick recap of the SDSS camera. It has 6 columns, 5 filters, and it's a time delay integration mode in which the sky processes the static camera, and the lines are integrated from the entire chip and then read out at the end. Once the trail is, and the meteor can cross this CCD array in any which way it can happen. And to reconstruct the trail, you have to account for the fact that there are several frames inside a CCD chip, and that the trail can cross several different CCD chips in different camera columns and different filters as well. And once we can reconstruct the trail, we can actually get to the scientific part. The first things you notice is that the initial trail sections are usually are usually look more like lines and a single object than the latter part of the ending part of the trail, and that is mostly due to defocusing effects. And what you also can notice is that the upper part usually has some kind of dust and debris formation as well. The defocusing effects could potentially be deconvolved, and more than that, you can use this defocusing effect to try and estimate the height on which the meteor occurred. For SDSS, which are the full lines, you can see that these defocusing effects are much more pronounced than they will be for LSST, as far as the current specifications state. steps. Each is more computationally complex. And the primary focus of each previous step is to actually try and reduce all the pixels it can to zero, so that they are not active in the very computationally complex step of the line detection, which is done by Hopf transform. That step actually basically is per pixel, so you want to have the final image as empty as possible. One of the things that had to be done is to have an algorithm that is very optimized, because there will be a lot of pictures, and as far as I understood it, the allowed time in the processing pipeline should be very short. So I spent a lot of time doing it so that the actual algorithm would execute in less than a quarter of a second, which is what we had. And even for that, to process the SDSS pipeline, it takes about 20 days in total. And so we did that, but I repeat, as there are 29 different parameters that affect how the detection process works and what are the detection rates and what is the performance. This first pass of the SDSS was completely uneducated guess of those parameters, and not necessarily the actual best solution to the best detection rate you could achieve with the algorithm. So what are the things we could do from the results we get? And one of the things is we could do temporal distribution of the detected meteors. We could observe which times contain the largest peaks, and we could try and see if those times occur annually, and if they have some sort of periodicity to them, which could then be attributed to probably a meteor stream, most likely an unknown one, but possibly also an unknown one. And meteor streams also always have to have a parent body, which would indicate some parent body orbiting around the sun, which could be that, but it doesn't necessarily have to be, as was explained in the presentation before. We could also look at the light curves, and we could observe different kinds of light curves for different kinds of filters of SDSS. Just for a short reminder, this is filter transmission of the SDSS in its bands, UGR-IZ. The work on meteor spectra is still relatively new. The most important work was probably done by Borovichka somewhere in 1998, and that one still used VHS tapes to record the meteors. So it's kind of funny how such an old astronomy field is basically still so obsolete as far as technically wise, at least. Well, anyhow, we can observe the number of meteors in different wavelengths and see how that population behaves. There's a caveat to this and this image, which I seem to forgot to mention, and it's that the SDSS and LSST as well doesn't record just meteors. It records satellites as well, and they're the second prime number of detections we have, and a set of satellites basically consists of which is always time consuming, but I'm hoping that by the end of this year we'll devise that part of the algorithm that can automatically separate meteors from satellites. The thing as well to mention here is that this bottom graph represents the number of frames that was returned over on the dispersed paths of my algorithm over the SDSS database, and you can see how the number of false detections, mainly false detection, grows as we approach the Z-band and the longer data lengths. And I would probably attribute that most to the quality of noise in the image. As I said, there are several parameters that control that, but this run over the SDSS database was all done on the same parameters, and therefore this is most obviously not the optimal detection rate you could achieve with my algorithm. What is also visible is that there are less trails detected in the U-band, and that the number of trails stabilizes immediately after that. The estimates of 80% detected existing lines and 74% of all existing lines are based on the fact that this project was presented on an LSST conference, the first one in Cambridge, by Dan, but that one was based on an algorithm devised by Alexander Psychota, which was based on the RANSAC algorithm, and the detection rate of this magnitude was just unachievable. Just for R and I band, we then got about 500,000 possible detections, which we literally went through by hand in a time span of like a month. So, but in the end, they still served as a good base data comparison statistics, as a good base data starting point to see how my algorithm can handle such detections. And basically, I'm quite happy with these numbers, especially for a parameter set that was unoptimized, unminimized, and was just basically a guess. The thing that probably interests the LSST people is this slide, and it's a graph of number of frames done in a run, in a particular SDSS run, and the number of detections that were found in that run. So what this means is that this particular run had almost 10 to the third frame, so 1,000 frames, and it had this about 150 or so potential lines. That means that the expected this of course indicates that the expected percentage of frames in which you can expect to find a line is about 1%, and I believe that the LSST will have this number quite different, but probably similar. I mean that in the fact that the LSST time, imaging time, will be quite, as far as I understand it, longer than SDSS, and the field of view of the telescope is larger, so the probability that you'll see a meteor inside the field of view is also higher. Before I end, I'd like to just mention the differences between what my algorithm does on SDSS and what my algorithm does, and which parts of the algorithm should actually be run on LSST, because there's a large difference between the projects. The LSST will make my life quite easier because of the frame differencing, which means that basically the only thing you expect that will remain after frame differencing in the frame are the things that move and variable stars. And of course, detecting lines in such clean images is very simple because the largest obstacle to my line detection algorithm is the fact that there is so much junk left after I remove all known objects from the image, which I just do based on the catalog data alone. And of course, that's a very rough way to remove objects from the image. Additionally, the analysis of the meteor spectra will be much easier in LSST because you won't have to worry about blended objects. The trail, yes, of course, it will pass over different stars and different galaxies, but as long as the star of the galaxy isn't saturated by frame differencing, I believe that what we will end up was approximately the original trail data as well. So, in order to really, okay, so let's rephrase. I believe that the LSST can really benefit the meteor science in this aspect of telescopic meteors at least, because the magnitudes and the astrometry and the photometry precision that we could achieve on SDSS, or even if I run my algorithm in PanStars, or even if I run my algorithm somewhere else, the precision we can get is much higher than anything that is currently being done in the field of meteor science, at least. Thank you very much.
Okay, we've got time for one question.
I think it'll become about 5 times more, larger fraction of frames. The field of view is 10 degrees. SSS is 1 degree, exposure times 30 seconds.
1.5 or so.
Yeah. So I think when exposure times half. Well, obviously it's easier to do a difference imaging. We have a version of Huff transform, including a preprocessor involving second moments that works extremely well on the HSC data. So I think
Could you just pick up it?
I'm sorry. We actually will be delivering. We will be taking the trails out with moderately clever variation on Huff transforms to do this. You're not going to get any color information, however, unlike SPSS. So I don't know how useful this will be for your mutual cities.
I won't get any.
No, because you only get one band at a time. Slowly run RIUZ.
Yeah, but I mean, that's fine. Just the total populations per band also can indicate certain things, of course. And what do you mean you will be taking out trails?
Well, trails are garbage. I mean, so we have to remove them. Obviously, if you want to know about them, we can preserve information, and it'd be interesting to discuss what that information is that people would like. It's a very small data volume.
Yeah.
I think the broader emphasis, we will be identifying trails.
No, because when I spoke to Mario earlier, he mentioned only that you will be taking out the spurious. Yeah, thank you.
Taking the next speaker. Are there any other questions? If not, it's time for you.
that there are individual CCD frames may obscure one detection, but the second one will be there as well. We also added uncertainties in our astrometry and photometry as well to simulate reality of this. Another improvement was adding false detections. That's important, especially if you are trying to create tracks and orbits at the end, because all these false detections that are in those focal plane will create false fragments and false tracks, and will at the end kind of systematically or rapidly increase the number of false tracks. So on the right, again, there is an image showing not just the real asteroids in the simulation, but also the red dots and the blue dots is the noise. Also, we try to realistically take a look on limiting magnitude, because every single field that we use in our simulation has some limiting magnitude, but in fact it's not a straight path. It's not a straight path. It's not like your limiting magnitude is 25. In reality, it's kind of a probability density function, which means that limiting magnitude have a 50% probability that an detection there. And also, we employed trailing losses for our moving targets. NEOs are especially those objects that are moving a lot fast in your images, especially if they are close. So if you can have a detection loss, a single detection can be visible on multiple pixels. So if you compare that brightness per pixel with your binaries, of course it will be fainter in the image because of the motion. So that has to be included as well in the simulation. One of the interesting effects is vignetting. That is also losing some magnitude to your detection, especially near the edges of your focal plane. So the red color is actually showing the magnitude loss because of vignetting. And at the end, interestingly, asteroids are relatively interesting objects, having shapes and rotating around the axis, so they are changing magnitude as a function of time. So we simulated those asteroids rotation with a really simple approximation of the sine wave. On the top, there are some biased distribution of amplitude superior asteroids that we use for every single object we had in our simulation. And also we simulated colors, because asteroids don't have the same color. So we divided our population into two populations. One is C, one is S class. And every single population has a different transformation to the V, as mentioned in this table on the top. So what are our inputs? We used OPSIM surveys, 3 of them. One was the baseline, Enigma 1189, and 2 other surveys, I call them 3 and 4 visits. Those were optimized for 3 and 4 visits of the same field per night. So this histogram just shows the number of visits of a single field per night. And as you can see there is a significant amount of singletons that are unfortunately not really useful for solar system survey, because if you just have one image, you can have one detection of an asteroid, but you cannot get any tracklet out of that. We also removed those so-called singletons and deep green cosmology fields from our survey. So what are the results? Of course, it's not easy really to run many simulations for all 10 years with let's say 200,000 asteroids. So we made kind of a simplification. We only do 3,000 NEOs randomly from our population and simulated them through 10 years. And to somehow take a look if our approach is correct, we also ran one full simulation with all those 200,000 asteroids. And this plot is just showing the comparison between the, let's say, low fidelity 3,000 and high fidelity simulation of NEOs, 260,000 asteroids, and they match pretty well. All these lines that you can see on this colorful plot, they are showing efficiency as a function of absolute magnitude on the bottom. So detected means at least in one detection, then at least in one tracklet, then in 2-3 tracklets, and at the bottom, those curves represent tracks that span up to 12 days or up to 20 days. So this is the same plot. This is the plot for baseline survey, and as you can see, approximately, if you go to, let's say, 20-second absolute magnitude, which represents approximately 140 sites per object, based on our simulation, it shows that detection efficiency for tracks is between 60 to 62%, depending on surveys that are kind of optimized to 3 and 4 visits, you will lose a lot in detection efficiency. So if we add all those effects together, and if we don't use it, so this plot is showing what if you ignore all these tiny effects like Bradley loss, fading, vigneting, light variation, or colors of asteroids, you will lose only, let's say, 2% with respect to not using all these effects. Like the solid curve only uses fill factor and limiting magnitude, and the dash curves are using all the effects together. But mostly, most of the loss is given in the Bradley loss. So maybe 2 more plots to show. This is an interesting kind of case where we kind of made the limiting magnitude worse, because all the limiting magnitudes in the surveys are theoretical. So what happens if your limiting magnitude is systematically 0.2 or even 0.5 magnitude worse as expected? And it's shown in this figure, it will really hurt performance of searching for NEOs. On the last figure, we know NEOs are relatively fast, so it really depends on how fast can you go in your image to distinguish individual trails. So if you, let's say, take into account only objects that are moving slower than 2 degrees per day, you won't see a much difference if you stretch it to 5 degrees per day. You'll have a much worse results if you push it even down to, let's say, 1 or 4.5 degrees per day for any of those. And there is also a poster, this here on the right,